using structs to structure related data. A struct, or structure, is a common data type that lets you name and package together multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with a struct's data. Just kidding. Structs and enums discussed in Chapter 6 are the building blocks for creating new types in your program's domain to take full advantage of Rust's compile time type checking. Defining and instantiating structs. Structs are similar to tuples, which were discussed in Chapter 3. Like tuples or tuples, the pieces of a struct can be different types. Unlike with tuples, you'll name each piece of data so it's clear what the values mean. As a result of these names, structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then, inside curly brackets, we define the names and types of the pieces of data, which we call fields. For example, listing 5.1 shows a struct that stores information about a user account. So struct user, the fields are username, email, sign-in count, and active. And for the types, the fields are string, U64, and bool. So I see that they are using this comma after the last field, which is not necessary, but I like it because it feels consistent. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct, and then add curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template with particular data to create values with that type. For example, we can declare a particular user as shown in listing 5.2. Let user1 equal user, email string from someone at example.com, username string from some username 123, active true, sign-in count 1. To get a specific value from a struct, we can use dot notation. If we wanted just this user's email address, we could use user1.email wherever we wanted to use this value. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Listing 5.3 shows how to change the value in the email field of a mutable user instance. So we have let user equal, no, let mute user 1 equal an instance of a user type with email, username, and the rest. And then below that, user1.email equals, and then string from another email at example.com. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. Listing 5.4 shows a BuildUser function that returns a user instance with the given email and username. The active field gets the value of true, and the sign-in count gets the value of 1. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. Using the field init shorthand when variables and fields have the same name. That is here. Because the parameter names and the struct field names are exactly the same in listing 5.4, we can use the field init shorthand syntax to rewrite BuildUser so that it behaves exactly the same but doesn't have the repetition of email and username as shown in listing 5.5. So we have, active is given the value of true, and sign-in count is given the value of 1, but email and username are not okay. Yeah. Oh, I see. So the BuildUser function takes email and username as parameters. It takes them as arguments. Huh. That's pretty nifty. So in listing 5.5, a BuildUser function that uses the field init shorthand because the email and username parameters have the same name as struct fields. Here we're creating a new instance of the user struct which has a field named email. We want to set the email field's value to the value in the email parameter of the BuildUser function. Because the email field and the email parameter have the same name, we only need to write email rather than email. Creating instances from other instances with struct update syntax. It's often useful to create a new instance of a struct that uses most of an old instance's values but changes some. You will do this using struct update syntax. First, listing 5.6 shows how we create a new user instance in user2 without the update syntax. We set new values for email and username, but otherwise use the same values from user1 that we created in listing 5.2. So for example, for user2's sign-in count, it says sign-in count user1 dot sign-in count. So it's using the field value from user1. Using struct update syntax, we can achieve the same effect with less code, as shown in listing 5.7. The syntax ... specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. So for user 2, we have a new email value and a new username value, but we want to keep the active field and the sign-in count field from user 1. Listing 5.7, using struct update syntax to set new email and username values for user instance, but use the rest of the values from the fields of the instance in the user1 variable. Using tuple structs without named fields to create different types. You can also define structs that look similar to tuples called tuple structs. Tuple structs have the added meaning the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple be a different type from other tuples, and naming each field as in a regular struct would be verbose or redundant. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here are definitions and usages of two tuple structs named color and point. Struct color takes 3 fields of I32. Struct point takes 3 fields of I32. I should say consists of. Yeah, struct color has or contains 3 fields. Struct point has 3 fields, all I32s. So these are both basically just tuples, but we're creating them as structs because we want to be able to talk about different colors and different points and basically be able to just treat it like a tuple. But we need the different types. We need color to be a type, and we need point to be a type. Let black equal color. So we're using the same So this is a capital C. That is different. Okay, so we have let black equal capital C color with the fields 0, 0, and 0. Let origin equal capital P point with fields 0, 0, and 0. So here we have the fields have the same values, but the black color and the origin point need to be different types. Okay, so note that the black and origin values are different types because they are instances of different tuple structs. Each struct you defined is its own type, even though the fields within the struct have the same types. Even though in this instance, each of these two structs is its own type, even though the fields within the struct have the same types. So for an example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of 3 I32 values. Otherwise, tuple struct instances behave like tuples. Yeah, okay. You can destructure them into their individual pieces. You can use a dot followed by the index to access an individual value, and so on. So is this like tuple syntax? I don't remember tuples looking like that, but I don't remember much. Unitlikestructs without any fields. Oh, look at that. Have a main function. You can also define structs that don't have any fields. These are called Unitlikestructs because they behave similarly to what? That's a closed paren. Open and closed parens, right? They behave similarly to open and closed parentheses, the unit type. Unitlikestructs can be useful in situations in which you need to implement a trait on some object, but don't have any data that you want to store in the type itself. See Chapter 10. Okay. Ownership of struct data. In the user struct definition in listing 5.1, we used the owned string type rather than the slice type, the string slice type. This is a deliberate choice because we want instances of this struct to own all of their data. This is a deliberate choice because we want an instance of this struct to own all its data, and for that data to be valid for as long as the entire struct is valid. It's possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in Chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetimes, like this, which won't work. So we have a struct user, so we're declaring the struct. Here's what a struct. This struct user is different. Yeah, that must be why. I probably commented it out because it was giving me errors. Okay, so we can say struct user will have the following fields, same fields there, but the value for each of these fields is going to be, well, okay, so we have the value for the username and the email fields will be string slices. And then in f and main, we have let user1 equal user, email, a string slice, username, a string slice, active true, signed and count 1. The compiler will complain that it needs lifetime specifiers. Yeah, username expected a lifetime specifier. Missing lifetime specifier. In Chapter 10, we'll discuss how to fix these errors so you can store references in structs. But for now, we'll fix errors like these using owned types like string instead of references like string slices. An example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start with single variables and then refactor the program until we're using structs instead. We'll make a binary project with cargo called rectangles that will take the width and height of a rectangle specified in pixels and calculate the area of the rectangle. Listing 5.8 shows a short program with one way of doing exactly that in our project's source mainers. So we have a main function, let width 1 be 30, let height 1 be 50, and then println. The area of the rectangle is, which I knew what to call this. Variable, it's somewhere it was described as like little crab claws. So when I see it, I think of Ferris. But I don't know. I want a word for that. I don't know what to call it. So the area of the rectangle is square pixels, and is area, which, area function, right? Yeah, area function taking width 1 and height 1 as arguments. Below that is f an area. It takes width as a U32 and height as a U32, and results in a U32, which is width times height. Width times height. Listing 5.8, calculating the area of a rectangle specified by separate width and height values. Now let's run this program using cargo run. I think I'm going to do it this way. Go, am I in projects? I am not. Struct example. Here we are. Gosh, I can't type. Cargo run. The area of the rectangle is 1500 square pixels. I'll just put that right there. Make sure I block important things. Yeah, so even though listing 5.8 works and figures out the area of the rectangle by calling the area function with each dimension, we can do better. The width and the height are related to each other. Ding, 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 they should go in a struct, because together they describe one rectangle. The issue with this code is evident in the signature of area. The area function is supposed to calculate the area of one rectangle, but the function we wrote has two parameters. Oof. Yeah. I agree. The parameters are related, but that's not expressed anywhere in our program. It would be more readable and more manageable to group width and height together. We've already discussed one way we might do that in the tuple type section of chapter 3 by using tuples. Well, we'll do it now. Okay. Listing 5.9 shows another version of our program that uses tuples. So in this incrementally better example, we have function main, let rect1 be a tuple of 30, 50. Println, the area of the rectangle is square pixels. Square pixels. And then that is area of rect1. And down below, function area takes dimensions. Oh, I see, yes. Okay, so it takes, so function area, yeah. This is, I was confused about this a little bit before. It's becoming clearer to me now, I suppose. So here in a function definition, we can just instantiate a variable right here in the parameters field. So like, we're always using this let. Am I recording? Yes, I am. I have to go back and see why we use this let so much, because other times they don't use it and it seems to work. Let's try that now. What happens if I just say rect1 instead of okay, so it's necessary. What does it say? Oh, yeah, okay, that makes sense, because when I've seen them not use let, it was when they were talking about variables and immutability, and they had, like, you know, let x equal 5 and then x equal 6. So yeah, let is instantiating a variable, bringing a variable into scope, but here in the signature of a function, you can instantiate a new variable, like dimensions here. Then you state the type, which is necessary. You have to state the types, right? So you're instantiating a new variable, dimensions. It is a tuple of U32s. Oh, it's a tuple of U32s. Oh, little tuple of them. And then, results in U32. And down here, within the function, they're using their tuple called dimensions, and they never let it. They never let dimensions. So you don't have to use let in the parameter definition for a function. I was confused about that before. Not that I thought you needed to use let, but I saw this and I was like, well, where's dimensions coming from? What is that? Oh, well, we're instantiating it right here, because you don't have to say let if you're inside the parameter section of a function's definition. So listing 5.9, specifying the width and height of the rectangle with a tuple. In one way, this program is better. Tuples let us add a bit of structure, and we are now passing just one argument. But in another way, this version is less clear. Oh, it's getting worse. I don't know if I ran it with this. I don't know if I cargo ran it with this one yet. Let's try it. Yep, okay. I want a new line. Pardon me while I get in here and put a new line in my print one. Yes, much better. Ah, that's not what I wanted. Now I have to find that. Now I have to find the directory again. So in one way this program is better, but in another way it's less clear. Tuples don't name their elements. So our calculation will struct tuples don't. They do the other thing, which is they name the tuple as a type. Right, okay, so in another way, so our calculation has become more confusing because we have to index into the parts of the tuple. Okay? It doesn't matter if we mix up width and height for the area calculation, but if we want to draw the rectangle on the screen, it would matter. We would have to keep in mind that width is the tuple index 0 and height is the tuple index 1. If someone else worked on this code, they would have to figure this out and keep it in mind as well. It would be easy to forget or mix up these values and cause errors because we haven't conveyed the meaning of our data in our code. Right, so the former example, which I should have pushed it instead of deleting it. Anyway, well, it's up here. Scrolling on up. So here it's plenty clear and yeah, easy to read, easy to maintain, but it is more typing than we want to do. So we try, okay, well, let's do it. Is it fewer lines of code? Let's see. So we have, I'm just going to eyeball it. Okay, 1, 2, 3, 4, 5. Wait a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lines of code, including the new lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We cut one line of code for the win. But what we gain in brevity, we lose in clarity. Yeah, we haven't conveyed the meaning of our data in our code. So you look, this could just go away. Oh, it's gone. Nope, come back. Okay. So if I up scroll, it's there. If I down scroll, it's gone. I can then click. Yay. We use structs to add meaning by labeling the data. Am I recording? Yes, I am. Just over 30 minutes. We can transform the tuple we're using into a data type with a name for the whole, as well as names for the parts, as shown in listing 510. So this is not where we want to have a struct tuple. We want just a struct, because we're naming the parts. So, struct rectangle, fields width and height with their types. Function main, let rect1 be rectangle with brackets. Yes, this is in creating an instance of the struct. Yes, and then we have, we got to name width and height here. And then println, the area of the rectangle is square pixels. Area, reference to rect1. Okay, so function area rectangle takes in a reference to a rectangle. Aha, I see what they did there. And then it results in a U32. So here in this function we're creating a variable called rectangle, which takes a reference to a rectangle. And then the function looks in the rectangle struct and says, well, give me the width, which is not there, it's here. Yo, they called this rectangle with a capital R. Why? I don't understand. Okay. Rectangle.width is going to be 30, rectangle.height is going to be 50. So then multiply them, gives us the area. Here we've defined a struct and named it rectangle. Inside the curly brackets, we define the fields as width and height, both of which have type U32. Then, in main, we created a particular instance of rectangle with a capital R, which it confuses me. Or I guess because it's in the heap. Did I say that before? I'm speculating that variables with capital letters, variables that begin with capital letters are in the heap, whereas variables that use lowercase letters are in the stack. I want to say in the heap and on the stack. Okay, our area function is now defined with one parameter, which we have named a rectangle with a lowercase r, and here it is a reference to a rectangle. So this reference is on the stack, and I've been thinking about this symbol, the ampersand, for referencing, and I've gone through a few ideas. I'm not quite sold on calling it borrowing, but I've been knocking around a couple other ideas. Like one idea that I have is that so rect1, let rect1 equal rectangle, and a struct is going to be, is there any reason this has to be in the heap? Are structs always in the heap? This. Yeah, yeah, it's in the heap because, okay, anyway, I digress. So let rect1 equal rectangle, we'll assume it's in the heap. And then when we print it, area has to take a reference to rect1. So what it's taking is the reference, and you can think of the reference as this ampersand. So we do say reference to what, so we put rect1 here, but it's as if rect1, it's like this, let's see, so create a struct named rectangle. You were like, okay, all right, I'm following you. Are you getting to a point? And I'm like, yeah, hold on, watch me struggle to type for a couple of minutes, and then we'll get there, I promise. Okay. Bad at the Vim. So width, and width is an U 32. Yes. And so my number keys are not labeled. Nothing on my keyboard is labeled because I'm using a different layout. So when you see me, when I pause like this and I think, and then I type it, and then I congratulate myself because I typed it in because I got it right, it's not because I was looking down, guys. It's because I was thinking and remembering where what is. Okay, so then in f and main we've got let rect equal, it's going to be a rectangle, and then see, I wasn't going to use this is in Vim, near Vim. I wasn't going to use this because I used this instead of VS Code because I wasn't going to type in this video, but here I am typing. So width is going to be 30 and height is 50. Yes. Oh, I see that. The wrong thing. What has happened? Okay. And now go down here to our function area. So we're not taking dimensions, we're taking a rectangle. So change inner parentheses rectangle, which is a reference to the perhaps unfortunately named rectangle with a capital R. And here we're going to multiply. We're going to autocomplete anything? No, I don't have that set up. I used to. I don't think I'm going to tell you what I did to my configuration files, but I'll let you take a guess if you're curious. No, if you're curious. If you know stuff about Git and you're familiar with people using Git to manage their configuration files, and now you imagine me. I use Git, but just sort of the same way I do lots of stuff, which is learn by doing, and I make lots of mistakes. So How do you think I shot myself in the foot with git? What's the nastiest git command that a noob shouldn't use? All right, so we've got, this should compile. What's going on? Did I misspell something? Cannot multiply an I32 to a find an I for me. Find another one. Is there a key? Can I just go like this? Like a in? No, it doesn't do it. Okay, find another I. Wait a minute now. Could I say find the second I like this? F2. No. How about 2FI? Does that work? 2, find an I. Hey, I did it. Change it to a U. Okay. Wait, what? Right. Did I just write that to backslash? I do that a lot. Let's find out. No, I didn't. I guess I just didn't give it enough time. Okay. So I was talking about the ampersand, the reference character. It's as if it's as if, so area, it's a function and it has its has this little black hole right here where scopes fall in. So like main is saying, oh, I can see as far as the braces. Yay, I can see everything because I'm main. And then we've got, you know, a rectangle in the heap named rect1, and here comes a println and bouncing along, and then the area function. There's a hole, and rect1, that's not where I was. Oh, come on. End of word, okay. Yikes. Rect1 could fall in the hole. Well, this won't compile because, of course, I mean, hey, why not? Let me go here and just say we'll take the whole thing. So, so now, rect1 fell in a hole. Well, we want rect1. I mean, we presume that we're going to do something besides calculate its area. So, instead of letting rect1 go in that hole, we will say, we'll give it an ampersand instead. And the ampersand goes in the hole. So we still have rect1. Well, of course, you know, we only have one function. We only have one variable here, rect1, but there could be a bunch, and so we need to tell it which ampersand is going in the hole. So it's the ampersand. And it is a reference to rect1. So then we see that down here, the only thing that's really the same between this function's parameter specification and the argument we're giving it is the ampersand. So it's not asking for rect1, it's asking for the ampersand. Now, of course, it wants a special ampersand. It wants an ampersand to a rectangle. And we have the structure rectangle up here, right? So I think of it, I've thought of it several ways. One way I thought of it is that rect1 is a treasure, and this reference, how about this? Rect1 is a house. Yes, let's say rect1 is my house. So maybe instead of talking about borrowing, it will be clear to me if instead I think of it as like contracting something. So I've got rect1, I got my house. I need to know what the area is, so I get this area sort of function, area contractor function, and I say, okay, area, I need you to tell me what my area is. So I give him the dimensions of my house, my rectangle, but I don't want him to do anything to it. I just want him to, he just needs to look at it. He doesn't need to be able to change it. I don't want him swinging a hammer. I just want him, you know, taking a look at it. So this is like a contract with area, where area does something for main, I guess. Subcontractor. I was doing it for Println, which is subcontracted under main. Okay, anyway, so area is accepting this, and this kind of contract is specific to, in the terms of the contract, area is going to do its job without modifying anything, because it doesn't need to. Another contractor might bring his tools, you know, and I don't know, fix the house or do whatever else. Yeah, what if a contractor has come to build a room onto my house, and then rect one isn't mutable, so you couldn't. But I could conceivably make rect1 mutable and then have a contractor who's coming to build a room onto my house, right? And I need area to come out and calculate the area of my house twice, let's say. So the first time area comes out, takes this little, you know, reference to the house. But the house then is still there. Like the reference, the ampersand dropped in the hole, because that's what area needs, is just the ampersand. It doesn't need rect1. So rect1 is still sitting right here, jolly in scope. And of course, we have to imagine it's mutable. I'm not going to type it in now, but don't have another function come along and say, you know, adjust the width. Maybe we'll make the width 40. And then that function would actually need a mutable. It would need it. It would need to, as they say, own it for the duration of its scope. And then after that function is done, Println can come back in, and Println still doesn't, I mean not Println, area still doesn't need the actual house. Area just needs a reference to the house. So then when the reference drops back in to area's argument hole, then it'll point back to, I don't know, I sort of rambled for a while there, but I trying to understand this, I hit a problem thinking of it as borrowing. I've also thought about treasure and treasure maps. I thought about, instead of calling it borrowing, calling it scry, you know, hashtag nerdlife. Like maybe rect area doesn't need rect1, it just needs to scry. It needs to scry rect1. So area is like not even there, right? So it can just, yeah. Am I still recording? And how long have I been going? It's getting close to 50 minutes. How about I keep going until there's a new chunk of code? Yeah. So here we have defined a struct and named it rectangle. I think I read this. Yeah, well, I'll keep reading. Inside the curly braces, we defined the fields as width and height, both of which have type U32. Then in main, we created a particular instance of rectangle. Yeah, I did read this because I fussed about a capital R. That has a width of 30 and a height of 50. Our area function is now defined with one parameter, which we have named rectangle. As we mentioned in chapter 4, we want to borrow the struct, we want to scry, I'll just try using these words. We want to scry the struct rather than take ownership of it. This way, main retains its ownership and can continue using rect1, which is the reason we use scry in the function signature and where we call the function. I wonder if calling this scry came up in the like the language team meeting, and they were like, "Oh, come on, we'll call it scry." And then some clear heads prevailed and said, "No, borrow's not perfect, but we're gonna have to call it borrow." The area function accesses the width and height fields of the rectangle instance. Our function signature for area now says exactly what we mean. Calculate the area of rectangle using its width and height fields. This conveys that the width and height are related to each other and it gives descriptive names to the values rather than using the tuple index values 0 and 1. Clarity for the win. I forgot to scroll down. Okay, here we go. Down scroll. Oh no. Stop doing. Go away. What have I done? Oop, just kidding. No, that should have worked. What the? No, control? Shift. Oh, come on. Oh, here we are. And then use my little Vim keys. Oh gosh, there's a bit there. Okay, so, oh snap, here we go. Adding useful functionality with derived traits. I'll have to pick this up here next time.